In this video, I'm going to go over the solution to the Carnot cycle problem I set up in the video before. In this problem, we have 1 kilogram of water in a piston cylinder assembly going through the Carnot cycle. In this video, I'm going to change this temperature right here from 40 degrees Celsius to 50 degrees Celsius. So I'm going to jump right in and start covering part A. And right now I'm going to focus on finding the temperature and pressure at each state. And we have 4 states, 1, 2, 3, and 4. So at state 1, the water starts off as a saturated liquid at 150 degrees Celsius. Now, it starts off as a saturated liquid, and so when we're given the temperature, there is one corresponding pressure that this saturated liquid can be at. And so for this problem, we're going to be relying a lot on the saturation table for water. And I've got one right here. So we'll go to, so this is a saturated table for water. And here we can see at 150 degrees Celsius, the pressure will be at 4.758 bar. So I'm going to keep track of our values in this table right here. Okay, so the temperature at state 1 was at 150 degrees Celsius, and from the table we saw that it was at 4.758 bar, which is also equal to 475.8 kilopascals. So temperature will be in C, and our pressure will be in kilopascals. Okay, so if you remember, from state 1 to state 2, all of the saturated liquid becomes saturated vapor, but it occurs as an isothermal process. So in state 2, we're still at 150 degrees Celsius, and that means the process also occurs at a constant pressure. So that will be also 475.8 kilopascals, which is just another unit for pressure. Now at 3, we are at 50 degrees Celsius. So now if we go to our table, at 50 degrees Celsius, we're at 0.1235 bar, which is also 12.35 kilopascals. So here, so here we are at 12.35 kilopascals. Now again, the process from 3 to 4 is also an isothermal process. So at state 4, we're at 50 degrees Celsius and also at 12.35 kilopascals. So process from 1 to 2 was isothermal and 3 to 4 was isothermal. Okay, so that was most of part A, and that was mainly just looking at the saturated table for water. So now for the tricky part. In part B, we're going to be calculating the change in internal energy, the Q in, and the work for each of these 4 processes. So as a reminder of one of our fundamental laws, the change in internal energy is equal to Q in minus work. And here, work is defined as positive when work is done by the gas. So here, work is positive when work is done by the gas, and it is negative when work is done on the gas. So this will become clear as we work through some of the calculations for these processes. So let's start the process from 1 to 2. So this is an isothermal process. It also occurs at a constant pressure. So we're going to start with, so change in internal energy from 1 to 2 is equal to Qin minus work from 1 to 2. Now I'm going to focus on first trying to calculate the work from 1 to 2. So here, from work to 1 to 2, this process occurs at a constant pressure. So we have pressure times specific volume at state 2 minus specific volume at state 1 times the mass. So here we have pressure, and at state 2 we're going to use the specific volume. At state 2 will be gas. At state 2, remember, it is all gas at 150 degrees Celsius minus the specific volume of a liquid, saturated liquid at 150 degrees Celsius multiplied by the mass. So here I'm going to plug in our values. So here we have 475.8 kilopascals times, and here I'm grabbing these values again from our table. So here I'm looking at the 150 column, and here we have specific volume values for a liquid at 150 degrees Celsius and for vapor. So all the values I'll be grabbing are from this row right here and in the row in the 50 degree case. And again, the link is posted underneath this video. So back over here, specific volume value for the gas at 150 degrees Celsius is 0.39 minus 1.0905 times 10 to the negative 3, and the units of this is meters cubed per kilogram, and we have 1 kilogram in our system. So here the kilograms cancel out, and when we multiply all this out, we get 186.4 kilojoules. So what kilopascals times meters cubed will get us the unit of kilojoules, which is a unit of energy. So this is the work done by the gas. It is a positive value, so we know the work is being done by the gas, which makes sense because in this state, from 1 to 2, as it starts off as a saturated liquid, it pushes against the piston, turning into a vapor. Okay, so here we can put 186.4. And all the values in this table will be in kilojoules. Okay, so now let us calculate the change in internal energy from 1 to 2. So this is simply going to be the internal energy of the gas at 150 degrees C minus the internal energy. So in the table they have F, which basically means as a liquid. of 150 degrees C. And the units of this is kilojoules over kilogram. So we're going to multiply this by, we've got 1 kilogram of mass. Sorry, the units of this was kilojoules over kilogram. So kilogram cancels out. And if we plug in the values from the table, we will get 1927.8 kilojoules. Okay, so here we have 1927.8. So back to this law, our Q in is going to equal the change in internal energy from 1 to 2, or this should be an equal, plus the work from 1 to 2. So if we add these two values up, we will get 2,104.2 kilojoules. So now, there's something very interesting about this value. If we go back in this table, we'll find that this is also equal to the enthalpy of vaporization at 150 degrees Celsius, which is also the symbol for this is HFG 1 degrees Celsius. So this is the amount of energy required to convert a liquid to gas at 150 degrees C. And there's already a known value for this energy, and that is right here. So this is the HF of G is the enthalpy of vaporization. And so this is the energy it requires to convert a liquid at one temperature to a gas at the same temperature. And for 150 degrees Celsius, it is this value, which is what we had calculated. And so those two match up as they should. So that's kind of a check. Okay, so that was the process from 1 to 2. Now we're going to work on the calculation from 2 to 3. Oh, one more thing that I want to do for this process that we'll use later on is let's calculate the change in entropy. So the change in entropy for this process is again Sg, and again this is from the table, fluid at 150 degrees Celsius, and we'll multiply this by our mass, which is 1 kilogram. Units of this is kilojoules per kilogram, and here kilojoules per. So here we are going to get the change in entropy in this process was approximately 5 kilojoules per Kelvin. And we will use this later. So I'm going to just have a here where we're tracking, and this is kilojoules per Kelvin. So here it was a positive 5. Okay, so now let's go work on the process from 2 to 3. So I'm going to erase all of this. Okay, there we go. Okay, so now let's do the process from 2 to 3. So this one, if you remember from your Carnot cycle, this process is isentropic, and no heat exchange. No heat exchange. So here our equation is going to be change in internal energy equals Q minus W. Here though, we don't have a Q. And so our change in internal energy from 2 to 3 will also be equal to negative of the work from 2 to 3. So since this is an isentropic process, the entropy at state 3 will have the same entropy at state 2. So if we look in our table, Sg, so at state 2 it is all vapor at 150 degrees Celsius, and that is equal to 6.8379 kilojoules per Kelvin. And so the entropy at state 3 has to have the same entropy. Now at state 3 it's going to be a mixture of vapor and liquid, but we don't know exactly how much yet. So here I'm going to call mv3 as a vapor, the mass of vapor at state 3, and we'll have ml3 as the mass of the liquid at state 3. Now I know that both of these has to equal to 1 because we have 1 kilogram. We start off with 1 kilogram of water, and this needs to be conserved throughout this entire process. Now I also know that, so at state 3, I also know that my mixture has to be at 50 degrees Celsius. And so another equation that we can use, and I also know that the total entropy at state 3 also has to equal to the entropy it was at state 2. So my second equation is going to look like this. 50 degrees C times the mass of the vapor at 3 plus entropy liquid at 50 degrees C times the mass of the liquid at 3 is going to equal to this value, 6.8379. So here I have a system of 2 equations and 2 unknowns. And so when I solve for this, I will get that the mass of V3 is equal to 0.832 kilograms. And the mass of the liquid at state 3 is 0.168 kilograms. So at state 3, we're still mostly vapor, but there is some liquid. Okay, so now that I know this ratio, it's pretty simple to now calculate the change in internal energy, which will simply be the mass of the vapor, 3, times internal energy at 50 degrees Celsius for the gas state, plus ml3 u F 50 degrees C. And so this right here represents internal energy at state 3, and I'm going to subtract this from the internal energy at state 2. This is simply by all of it. At state 2 is all vapor, so this is by times 1 kilogram. And so here I'm going to get that this is equal to 491.34, negative kilograms or kilojoules. This means, back to this relationship, that the work from 2 to 3 will be a positive 491.34 kilojoules. Again, this makes sense. It is positive as it should because the gas is still doing work from 2 to 3. So here we fill in a table, again, no Q from 2 to 3. So this should be, okay, we'll keep right here. 4, okay. Not what I wanted. $491.34. Okay. Sorry, technical difficulties here. These layers are a little tricky. I haven't quite figured out correct way to use this. But okay, so we can write it here. Okay. Does that work? Okay, so to make a note of those values. So now I'm going to carry on and work on the process from 3 to 4. From 3 to 4. So again, we've got our change in internal energy from 3 to 4 is equal to Q in minus work from 3, 4. So again, so if you remember that from 1 to 2, we had an entropy change of positive 5. So from the process from 3 to 4, we're going to go through the same entropy change, but this time our entropy is going to decrease by 5 kilojoules per Kelvin. So at state 3, we are at 6.837 kilojoules per Kelvin. At state 4, we will be 5 less than this. So we'll be at 1.8379 kilojoules per Kelvin. So again, we're going to do something similar as we did with process 2 to 3, and we'll have our mV4 plus mL4, so the mass of the vapor at state 4 and the mass of the liquid at state 4 both have to equal to 1. Now I also know that the SG 150 sorry, not 50, we're at 50 degrees Celsius plus let me rewrite this, sorry, SG 150 times the mass of the vapor at state 4 plus SL 150 times the mass of the liquid at 4 is equal to 1.8379. So again, I'm going to solve for using this system of 2 equations and 2 unknowns. I'm going to get that my mass at the vapor 4 is now going to be only 1.154 kilograms. But now the mass of my liquid has gone up to 0.846 kilograms. So in a similar way, now I can calculate the change, my internal energy from 3 to 4, in the similar way as I did from 2 to 3. So this is going to be equal to the mass at V4 UG at 50 degrees Celsius plus the mass of the liquid at state 4 U liquid 50 degrees Celsius. And sorry, sometimes I know I've been writing UL or SL. I know in the table I provided, I think L, they use F for L. So just know that I've been using that interchangeably. So this represents the internal energy at state 4. And then the last process I did, we had calculated U3. And so this is going to come out to be negative 1514.7 kilojoules. Now, if you remember we're going to calculate work in the same way that we did the process from 1 to 2. So work will be, again, change the pressure, which is in the process from 3 to 4, we are at 12.35 kilopascals the entire time. Then we're going to take our specific volume at state 4 minus V3, and this will be by the mass, which is 1 kilogram. And so you'll use these ratios to find V4 and V3, and this will come out to be negative 100.74 kilojoules. So that means that, so this is from 3 to 4, and this is the change in internal energy from 3 to 4. This is this. So that means that the Q is negative 1413.96 kilojoules using this relationship. And this makes sense because in the process from 3 to 4, we have a negative sign because heat is leaving the system. So that's the process from 3 to 4. So again, here's your change in internal energy, the work, and so again, the work here is negative, and that means that work is being done on the system. And so it's a good way to make sure that your signs make sense with the cycle that you're in the process on the cycle you're in. Okay, so now we're almost done. We're going to be doing the last one, and this one is not that bad. So the work from 4 to 1. So again, if we do our change in internal energy is equal to Q minus work from 4 to 1. Now this process has no heat exchange. So our internal energy from 4 to 1 is simply going to be negative the work from 4 to 1. So we just basically have to calculate the change in internal energy, which will be internal energy at 1 minus U at 4. Now if you remember, we had found this in our calculations from 1 to 2. And this one at state 1, it is all saturated liquid. So we can just use this value of UF150. That would just again be multiplied by 1 kilogram. And we had found this in our last problem, which was again, let me, 1 second. I think I should have that value. That one will be, so you should have gone this to be 553.38 kilojoules per kilogram. And again, we'll multiply this by our 1 kilogram. So this will come out to be negative 78, or sorry, positive 78.3 kilojoules. And so that means that our work from 4 to 1 is negative 78.3 kilojoules. And this was change in internal energy. Okay, so now that we've got, that was part B. I know that was a little long, but really all it comes down to is using the table correctly and your main law, change in internal energy equals to Q minus work, and really understanding how the sign of work works. Okay, so now the last part, efficiency, and seeing if our values match up. So one of the expressions for efficiency for the Carnot cycle is 1 minus Tc over Th. So we could have solved the efficiency for the cycle without having to do any of that work. So Tc is at 50 degrees Celsius. That's our cold temperature. And we need to convert this into Kelvin. So in Kelvin, this is equal to 323.15 Kelvin. Our Th was at 150 degrees Celsius, and this was 423.15 Kelvin. So if we plug these values in, we are going to get 23.6% efficiency. Okay, so now let's see if our values matched up. So this expression came from the definition we had for efficiency for cycles in the first place, which was the net work throughout the cycle over Q in. Basically, how much work are you getting out from the amount of heat that you put into the system? And so this will be work 1, 2 plus the work from 2 to 3 plus the work from 3 to 4 plus the work from 4 to 1 all over Q in. And this was the heat input from 1 to 2. So these two values, again, should be positive because this is when the system is doing work on the surroundings. These two values will be negative because work is being done on our system, which is what we had found. So if we plug in our values, we had 186.4, this is all going to be in kilojoules, plus 491.3 minus 100.74 minus 78.3. This is all over our Q in from 1 to 2 to 114.2, and if you put that all in your calculator, you will get 0.236, which matches up with this value. So that wasn't a very good circle, but so ta-da! So hopefully that gives you a better, more practice with the Carnot cycle and how to use saturated tables and applying that to this type of problem. Okay, thanks for watching. Bye.